Welcome to Study Loop.
Okay, so on this problem we have a proton and a alpha particle distance 0.225 nanometers apart. We're told that the alpha particle has 4 times the mass and 2 times the charge as the proton. So the proton has charge E, and mass of the proton, and the alpha particle has charge plus 2e and 4 times the mass of the proton. And all of those are constants that we're going to look up later. So we're told to calculate the maximum acceleration and velocity of each of the particles after they're released from each other this distance apart. So first thing that you should think of as a relevant equation is the force between two charged particles. That is 1 over 4 pi epsilon naught times the product of their charges divided by their distance squared. Okay, so this force is going to decrease as these two positively charged particles move apart from each other. So if we plot distance between them and force, they're going to start at 0.225 nanometers. They're going to have a certain force, and as they move apart, they're going to experience less and less force. So because F equals ma, the force and the acceleration are just proportional to each other. And so since the maximum force happens when they're first released, that's also when the maximum acceleration is going to happen. So we know that the maximum acceleration is happening when they're 0.225 nanometers apart. So we just need to calculate the force and divide by mass to get the maximum acceleration. So let's go on to another screen in order to plug in some numbers. If I can figure out how to do that. Okay, so we said that acceleration max is going to equal F max divided by the mass of whichever particle we're looking at. And from Newton's third law, we know that this max force is going to be the same for both particles, but opposite in direction. And we know that this F max is given by the equation we showed before here to be 1 over 4 pi epsilon naught times the product of the charges. Let's put Q proton and Q alpha particle as variables for now, divided by the distance between them squared, which we know now is just this 0.225 nanometers. Okay, so we can look up some of these constants and plug this in. So the charge of a proton is the same as the charge of an electron, is 1.602 times 10 to the minus 19 coulombs. We also need to know epsilon naught, which is 8.854 times 10 to the minus 12 coulombs squared per Newton meter squared. And we're going to look for all of these in SI units so that our life is easier. the mass of the proton we're also going to need for this part is 1.673 times 10 to the minus 27 kilograms. Okay, so now we just need to plug in all of these numbers. Let's see if I can move this to another screen. Probably not. Okay, so let's just plug them in from here. We know that acceleration max of, let's do the proton first, is this F max divided by the mass of the proton, which is going to be the mass of the proton, let's put that up front, is 1.673 times 10 to the minus 27 kilograms. I'm going to leave all the units out here, and maybe we'll look at them later. And then we just have to write out this force part. So 1 over 4 pi epsilon naught, which is 8.854 times 10 to the minus 12 times the product of their charges, which is going to be the electron charge times 2 times the electron charge, since we know the alpha particle is twice the charge of the proton, which is the same as 2 times the square of the electron charge. To simplify that a little bit, 1.602 times 10 to the minus 19. Okay, now I'm getting squished in the corner, but that's all squared because we have 2 times electron charge times 1 times electron charge. And that's all divided by their distance squared, which we're going to put that in meters because we're working in SI units. 0.225 nanometers is 0.225 times 10 to the minus 9 meters. And that needs to be squared too. Okay, so if we plug that into some sort of calculator, we can calculate that to be 5.45 times 10 to the 18, and we're calculating an acceleration. So that's going to be in units of meters per second squared, since we're in SI units. So this is the acceleration of the proton. We still need to calculate the acceleration of the alpha particle. But luckily we know that these forces are equal, which will simplify our calculation. So acceleration max of the alpha particle is going to be F max divided by mass of the alpha particle. And now we could just plug this all in again, but to save us a little bit of work, let's just write this as F max of the alpha particle divided by the mass of the proton, because that's what we know. That's this thing we just calculated, and then just multiply it by mass of proton divided by mass of the alpha particle. So this equals this just because we multiplied by mass of proton divided by mass of proton, which is 1. And we know this part is this answer we just calculated. This part, we're told the alpha particle is 4 times the mass of the proton. So this is just 1 divided by 4. And so this answer is just this answer divided by 4, which is approximately 1.36 times 10 to the 18 meters per second squared. Okay, and the question also asks where this maximum acceleration occurs, and like we said before, the force is highest when they're closest together because of this 1 divided by r squared term, and that is at this 0.225 nanometers when they're first released. Okay, so that's the acceleration part. Now we just need to do the velocity part. So since we know that this acceleration is going to be positive, no matter what r is, it's going to get smaller and smaller, but it's still going to be positive. That means that both particles are going to be speeding up from the time they're released until they reach infinity. So this maximum velocity is going to happen as far away apart as they can be because they're continually speeding up. So that answers the last part of the question already. We know that the maximum velocity is going to be at infinity and not when they're released. And we just need to calculate what that velocity is going to be. So from conservation of energy, we know that the potential energy of this this configuration is going to equal the sum of the kinetic energy of the particles when they're at infinity, and this is 0. So let's write that out. The kinetic energy of the proton plus the kinetic energy of the alpha particle equals this potential energy in the starting configuration. Since when the particles reach infinity, they don't have any potential energy. All of their energy is going to be in the kinetic energy. So what's the expression for this from your textbook? This is just 1 over 4 pi epsilon naught times the product of the charges divided by their distance. So this should look very familiar to the force equation. It's just divided by r instead of divided by r squared. Okay, so right now we have all of these numbers except for the final velocity of the two particles. And that's a problem because we only have one equation. We can't solve for two unknowns. So we need another equation. So the other thing you should know about the configuration is that momentum is conserved. There's no outside forces acting on either of these particles, just the forces from each other. And they're initially at rest. So the initial momentum is 0. So the final momentum when they're at their maximum velocities must also be 0. So that means that the mass of the proton times the velocity of the proton has to equal the mass of the alpha particle times the velocity of the alpha particle at all times, but also when they're at infinity, which is when we care about. So there could be a negative sign on one of these, but I'm going to treat these two velocities as just speeds as the absolute value of the velocity. So with this, we have two different equations and two unknowns, so we should be able to solve this. And to make our lives a little bit simpler, let's solve this for the velocity of the proton. Actually, let's solve it for velocity of the alpha particle, because I don't want to write this alpha more times. So the velocity of the alpha particle is just this divided by this. Mass proton, velocity proton divided by mass alpha particle. And as we saw before, the mass of the alpha particle divided by the mass of the proton is 4. So this is just velocity of the proton divided by 4. Okay, so now we can plug in for velocity of the alpha particle up in this top equation. I'm just going to copy the right part. This left term is going to stay the same. 1/2 times mass alpha particle times velocity alpha squared, which is this whole thing squared, So this 4 is going to be a 16 after it gets squared. And we can almost combine these terms, but we have a mass alpha here and a mass proton here, so we need to fix that. So let's use the same trick where we multiply by MP divided by MP, which is just 1. Okay, so let's times MP times M alpha divided by MP. So we haven't actually changed this term. At all. But we know this M alpha divided by MP is just 4. It's 4 times more massive. So let's call this 4. And now we can combine these like terms. So this is just 1/2 times these two things. This is, excuse me, 4 divided by 2 times 16. So 4 divided by 16 is 1/4. So this constant factor is 1/8. So we need to add 1/2 here and 1/8 here, which is, 4/8 plus 1/8, which is 5/8. So this is 5 divided by 8 m proton v proton squared. And you could just multiply, you could just plug in the numbers now that we have only one variable, but I wanted to algebraically simplify it a little bit so that we don't have to plug in as many numbers. Okay, so at this point we only have one variable. Our equation is this potential energy equals this kinetic energy. We just need to solve for Vp. Okay, so let's do that over in the corner here. So velocity proton squared equals 1/4 pi epsilon naught times the product of the charges. I'm going to write these out as Qp and Q alpha now, divided by R. And then you got to multiply by 1 over this to get this onto the other side. 8/5 MP. So if we wanted to solve for Vp, instead of Vp squared, we would just take the square root of this term. So let's, now all we need to do is plug in numbers. I'm going to go on to another slide to do that. So Vp equals square root, some of that went off the screen, 1/4 pi epsilon naught times, again, our product of our masses is 2 times the electron's mass squared, because the alpha product of the charge is not product of the masses, but the alpha particle's charge is just 2 times the electron charge. The proton's charge is 1 times the electron charge. Okay, that's all divided by R, and then you have to multiply this number 8/5 MP over 5 MP. Okay, so now we just need to plug in some numbers. I'm going to erase the edge of this so we can fit it in here. So this is just the square root of 1/4 pi times epsilon naught, which we said before was 8.854 times 10 to the minus 12 times 2 times electron charge squared, 1.602 times 10 to the minus 19 squared. Wow, that didn't come out very well. This was supposed to be squared minus 19 parentheses squared divided by r in SI units is 0.225 times 10 to the minus 9. And then we just need our 8 over 5 times mass of the proton, which we said was 1.673 times 10 to the minus 27 kilograms. Okay, so if you plug that all into a calculator, you will get 4.43 times 10 to the 4. Again, this time we're looking for a velocity, not an acceleration. So in SI units, this should be meters per second. Okay, so that's the velocity of the proton. The last thing we need is the velocity of the alpha particle. And that's easy because we found here that the velocity of the alpha particle is just the velocity of the proton divided by 4. So we just need to divide this answer by 4. And that comes out to be about 1.11 times 10 to the 4 meters per second. Okay, great. That was all the numbers we needed to calculate. We said that the maximum acceleration is when the particles are 0.225 nanometers apart, but the maximum velocity is when they're very far apart because they're constantly picking up speed. So that's all of the different parts of this problem. Thank you. There's a way to stop this. Okay, now I'm recording and I can't figure out how to stop it.